Hello everyone, and welcome to my senior research project presentation. Over the summer, I interned at the University of Maryland under the mentorship of Professor Clyde Krusko. I investigated improved methods of sampling for the Monte Carlo tree search algorithm, an algorithm that is used to solve sequentially based decision problems in applications such as games, robotic task planning, and scheduling problems. I shall now begin by giving some background information regarding artificial intelligence in games. The primary goal of artificial intelligence in games is to make the best decision at every point in the game. This is known as perfect play. While this is the goal, modern artificial intelligence game-playing programs commonly do not achieve this goal. For example, the supercomputer Deep Blue, while it achieved world championship level in the game of chess, it did not achieve perfect play. The algorithms used in Deep Blue consist of a mixture of min-max, alpha-beta pruning, and several heuristics present in chess. While these algorithms allow Deep Blue to achieve world championship level in the game of chess, these algorithms do not work very well in the game of Go. The game of Go is an ancient Chinese board game in which two players place pieces on the 19 by 19 grid in order to capture as much territory as possible. Now, the board size is 19 by 19. This is much larger than the chessboard, and therefore the branching factor is also much larger. This prohibits brute force from working effectively on this application. Another problem with the game of Go is that the intermediate positions in Go are difficult to evaluate. In chess, for example, you have each piece has an inherent value, and therefore you can evaluate intermediate position, and you don't have to brute force very far down the tree. But in Go, there's no standard way of saying how good or how bad an intermediate position is. Instead of brute force techniques, what we're going to do is use statistical techniques, such as Monte Carlo tree search, to apply artificial intelligence to the game of Go. Monte Carlo tree search relies on the assertion that if you play a move and then have many random games played from that move, eventually the random games will give you a good value of that move. For example, in a tic-tac-toe game, if I played the first move in the center spot versus the first move in the side spot, the corresponding amount of random games played from each location will be different. The amount of wins from the center spot will be much greater than the amount of wins from a side or a corner. Therefore, the value of the center spot in tic-tac-toe the value of the center is much higher in the center than in the side. Now, MCTS is separated into two policies, or two parts: the tree policy and the default policy. The tree policy decides which move you want to sample next, or you want to simulate next. And the default policy does actual game simulation and brings that value back up the tree. Note, this diagram is of MCTS run on the first move of a hex game. The hex game is a game where two players try to connect each side of the board with each other, trying to block the other player from connecting their two sides. Notice that these values are all very near 0.5, as values in MCTS tend to start at. As the game progresses, these values will go progressively near 1, signifying a win, or progressively near 0, signifying a loss. Now, to decide which move to sample next, MCTS uses a companion algorithm called Upper Confidence Bounds for Trees, or UCT. UCT is based off a solution to the multi-armed bandit problem. The multi-armed bandit problem is a thought problem in which a person is given the opportunity to pull 100 slot machines a limited amount of times. Now his goal is to maximize the amount of money he receives from these slot machines. So he has the choice of either pulling new ones to see if they're good, or exploiting the current best slot machine he knows of. This solution is known as cumulative regret, or minimizing, so to speak, because it maximizes the amount of money he earns throughout the entire duration of the sampling. This is in contrast to simple regret, which can be expressed as the money he would have earned on the last machine, or what it is applied to MCTS. In MCTS, we really only care about the last move we play, or the move we play during the game. So we don't really care about the simulations that made during the time we get to that solution. Therefore, we want to minimize simple regret and not cumulative regret. Therefore, and UCT is not the correct solution to this problem. In previous papers, many researchers mentioned that they used UCT as because it was empirically successful, but they did not. They never give a reason why it's a theoretical reason for why it's successful at all. In my research, I developed new methods that minimize simple regret and improve upon the concepts of UCT. So what we want to do is we want to minimize simple regret, or basically we want to sample the nodes that have the most impact on the result of the sample. So how do we do this? Well, an impact can be defined as either a new node becoming the new max, or the current max falling below another node. So basically, how many losses would I need to have the best move fall below the second best move, or how many wins I would have to have before another move becomes the next best move. So using these concepts, I created two formulas called the win-loss sampling scheme that dictate how many samples are needed the minimum amount of samples needed to impact the result of the current iteration. However, this sampling scheme isn't perfect. We also have to consider that the probability of wins and losses are not consistent based on different probabilities. Like if you have a moves with values of 0.9 and moves with value of 0.8 next to each other, while in another game you have values of 0.2 and 0.1, the chances of winning and losing are not the same, and therefore we must normalize this to get a better value. This normalization gives us the pure ratio sampling scheme, which works much better than the win-loss sampling scheme. The next sampling scheme comes from considering that extreme values, such as if you have a value of 0.9 versus a value of 0.5, it's very unlikely for the 0.9 to drop to 0.5. Therefore, we must normalize that too. We must consider that it's very unlikely for such a high value to drop very low. Therefore, we must exploit that as much as possible to find the right value. The last scheme I made is ASPRS, which is a combination of earlier schemes and simplified for efficiency and processing speed. Now, the benefits of these three methods are that they are all easier to calculate and they address the simple regret problem I mentioned earlier. To test these three methods, what I did was I created artificial trees and tested them on real games. So artificial trees, for artificial trees, I created randomly generated game trees, and then the goal of the program was to find the best path down these game trees. So each one of these artificial trees would generate 10,000 trials for these tests, and each method was also run many, many times on these artificial trees. Now, for games, I use Connect4 and Hex. So to test these schemes on games, on one player I implemented UCT, and then on the other player I implemented my scheme. So each of these schemes played 1,000 games against each other, and to adjust for the advantage of playing first, I alternate the starts between each game. So simple regret can be expressed as a numerical value, which is the difference between the best and the expected best. So in this first graph, you can notice that my two schemes, PRS and ACPRS, both perform much better than UCT, at almost an order of magnitude better as simple regret. Now, while ASPRS did not perform as well as the two schemes aforementioned, the ASPRS was optimized for speed and efficiency, so it is not as accurate as the two schemes. The next graph is a graph of the percent correct choices that the schemes made on the artificial trees. Notice that in the beginning of the graph, the schemes perform much better than UCT by almost 30%. The samples on the bottom indicate how many samples I run on the moves before I decide to play, before I decide to compare the results. So as the amount of samples increases, notice that UCT starts to approach my schemes. However, because this relationship is very asymptotic, the difference is much greater at that point than earlier. So for the games which I played two schemes against each other, I chose UCT and ACPRS as the candidates to play against each other. So in Connect 4, ACPRS performs significantly better than UCT at 1,000 simulations. When I increase the number of simulations to 10,000, ACPRS performs even better. This indicates that ACPRS approaches the correct solution to Connect 4 faster than UCT. Now, and the last example is Hex game, which, if you can notice, that ACPRS is much better than UCT. So the general results were that my schemes were much better than UCT in both simple regret and percent correct. They were better as the branches increased, and they gave good and fast estimates when samples were low. Another thing to note is that when I was running these programs, I did not specifically record it because the programs weren't optimized for runtime efficiency. It was that the new schemes run significantly faster than UCT, at the order of 2 or 3 times. This can be noted because UCT possesses the logarithm, which is hard to calculate, while my schemes only possess simple arithmetic. From this we can conclude that simple methods and not complex formulas can work as well as UCT. This implies that maybe even better methods based on simple concepts like simple regret can actually be better than UCT, and even better than my method. So future research should be directed to finding these new methods and optimizing these new methods for their applications. These faster optimizations can help several applications such as robotic path planning and scheduling problems, where speed is a necessity. I would like to acknowledge Professor Crusoe, my mentor, and Dr. Stone and Mr. Kern for the support they gave me during SRP. Any questions?